Section 4.7, Applied Optimization Problems. In this section, we're going to discuss how calculus can solve optimization problems. Optimization problems are problems that involve maximizing or minimizing a value. Examples of values we would want to maximize would be areas of a region with a fixed shape and perimeter, or profit. Values we would want to minimize would be materials that can be used to make a container with a fixed shape or volume, or cost. Now we're going to discuss a strategy to help us solve optimization problems. First, introduce all variables that you think you may need in the problem. To help you determine what variables you should introduce, try drawing a picture to help you visualize what is going on, especially in problems that involve geometry. Then determine which quantity is to be maximized or minimized and what the range of the values of the other variables are, assuming that they can be determined. Ideally, we would like to have variables to have closed intervals, but we'll talk more about that later. From there, you want to write a formula for the quantity to be maximized in terms of the variables. And keep in mind, this formula may involve more than one variable to start. In situations where the equation that we've derived in step 3 has many independent variables, we do want to write an equation relating the independent variables in the formula from step 3. Using these equations, we can rewrite the quantity to be optimized as a function of a single variable. Steps 1 through 4 can be the hardest part of the optimization problem. However, if you are organized with the information, drawing pictures, naming variables, looking at relationships between the variables, you will be able to find a function of one variable that can be optimized. From there, identify the domain of the function from step 4 based on the context of the problem. You want to make sure you are careful finding the domain of the function. You always want to keep in mind what is possible. For example, I cannot have negative length of an object. I cannot sell more items than I have. Make sure your domain includes everything that is possible, and don't try to restrict the domain to what you would do in a situation. Then step 6, locate the maximum and minimum value of your function from step 4. If the region is closed and bounded, we can accomplish this by using the extreme value theorem. We'll discuss what to do when the domain is not bounded and closed in later examples. In this problem, suppose a piece of cardboard measures 20 inches by 15 inches is formed into an open top box by cutting a square from each corner. Each square that is cut out have the same side length. What is the maximum volume that can be made from the piece of cardboard? What is the side lengths of the squares that are being cut out? Since the problem is telling us to maximize volume, that means we are working with an optimization problem. Since our optimization problem is involving geometry, we should draw a picture to help us understand the problem. First, we'll draw our piece of cardboard. We'll use this rectangle and we'll label the dimensions 15 by 20. We're told that we are cutting squares from the corner of each box. We'll let these white regions represent the squares we're cutting out. Since we're trying to determine the side lengths of the squares we're cutting out as part of the problem, we'll let x be the side lengths. And we're told that each square has the same side lengths. So each square is x by x. Now, how exactly will this box be formed? Well, after we cut the squares out, we're going to have what look like tabs left over in the cardboard. And we're going to fold those tabs along the blue line to form our box. Now let's start thinking about the range of possible values of x. It is possible that I decide to cut nothing out of the cardboard. Yes, I would not make a box, but it is possible. So for that reason, one of our possible x values is 0. What is the largest x value? I can't cut out more than what is available. If I consider what the lengths of each of these blue lines are, the vertical blue lines, because I'm cutting x and x out of a side length that is 15 originally, the vertical blue lines will have a length of 15 minus 2x. As for the horizontal, they'll have a length of 20 minus 2x. Since the vertical side is always going to be smaller, I'm going to run out of cardboard on the vertical side before I run out of cardboard on the horizontal side. So my 15 minus 2x must be greater than or equal to 0. I can make it 0 by just cutting x sufficiently large enough to completely get rid of that part. If we solve for x, we get that x is less than or equal to 7.5. So the possible values of x is 0 to 7.5. Now that we know the ranges of x, let's start making a formula to represent what we're trying to maximize. We're trying to optimize the volume of a box. Recall that volume equals length times width times height of that box. Because of how we're folding the horizontal and vertical tabs up to form the height of our box, the height of our box will be x units. As for the length and the width, those would be the dimensions of our blue base of our box. So we'll make the length 20 minus 2x and w 15 minus 2x. Now that we have h, l, and w in terms of x, we can plug them into our volume formula, and we'll have a function of volume that depends only on x. And our volume function will be x times 20 minus 2x times 15 minus 2x. The domain of our volume function will be the range of possible x values, which is 0 to 7.5. Since our volume function is a polynomial and our bounds are closed, we can apply the extreme value theorem to find our maximum volume. To help find our maximum volume, we need to find our derivative, but before that, we should expand to make it easier and avoid a triple product rule. When we expand, we get that v of x equals 4x cubed minus 70x squared plus 30x. Using power rule, we get that v prime of x equals 12x squared minus 140x plus 30. Since our functions are polynomials, then v prime of x will never be undefined. So we only need to worry about setting our derivative equal to 0. Since our derivative is quadratic, we can apply the quadratic formula. And after applying the quadratic formula, we get that x equals 35 plus or minus 5 root 13 over 6. Now we have to check to see if each of these critical numbers fit in our domain. For our result from the addition, we get about 8.8, but 8.8 does not lie between 0 and 7.5. So we'll drop 8.8. As for the minus, that'll be about 2.8, which does fall within the bounds of 0 to 7.5. So our only critical number is 35 minus 5 root 13 over 6. Now we'll plug our endpoints of our domain and our critical number into our volume function. And we're going to approximate the 35 minus 5 root 13 over 6 as 2.8, since most of the times in these problems, you are going to be rounding to a certain value. If we plug 0 or 7.5 into our volume formula, they will both give us 0, whereas if we plug in the 2 we get 379 as the volume. Now we can answer our two questions. What is the maximum volume of our box? That'll be 379 cubic inches. As for what the side lengths of the square we're cutting out will be, that would be 2.8 inches. Suppose I own a hotel with 100 rooms. When I set the price to stay in one of the rooms to $200 per night, every room is booked. I estimate that if I increase the price by $1 per night, then the number of booked rooms decreases by 2. What should I make the price of a room per night to maximize revenue? In this problem, we're trying to maximize revenue. Now, how exactly will we calculate revenue in this scenario? Because we're offering rooms at a certain price, our revenue would equal the number of rooms booked times the price per room. To help us understand how to construct our revenue function, we first want to start off naming a variable. Because we're manipulating the price, we're going to let x be the change in the price per room. To help us organize how x affects our price per room and the number of rooms booked, we're going to make a table. In this table, we're going to organize the price per room and the number of rooms booked before and after our price change. For the before, we're told every room is booked when the price is set at $200. So the price per room would be $200, and our rooms booked would be 1,000, since there's 1,000 rooms in the hotel. Since I'm increasing the price by X dollars, then my new price per room will be 200 plus X. But for every X dollars I increase the price, I booked 2 less rooms. So if my price increases by X dollars, then the number of rooms booked decreases by 2X rooms, meaning I'll have booked 1,000 minus 2X. Now we can start making our revenue function. Focusing on the price per rooms and the rooms booked after I make the change, we get that our revenue function, R of X, is equal to 200 plus X times 1,000 minus 2X. Now let's find the domain of our revenue function. To start, I could not change the price at all. So the lower bound of the domain would be 0. As for the upper bound, I cannot increase it so high that I stop booking rooms. Because once when I stop booking rooms, my revenue will just be 0. So my revenue function only makes sense while the number of rooms booked is greater than or equal to 0. If we solve this inequality, we get that 500 would have to be less than or equal to X. So the largest value I can make X is 500. Now that I have my domain, I know it's closed and bounded, so I know I can apply the method of finding the absolute extreme that we studied when we learned the extreme value theorem. So I have to start by finding my critical numbers, which means I need to find the derivative of my revenue function. Before I do, let's expand it so we can use power rule, and I get R of X equals negative 2X squared plus 600X plus 200,000. Differentiate our revenue function, and we get that R prime of X equals negative 400X plus 600. Since we're working with polynomials, our derivative can never be undefined, so we only need to set it equal to 0 and solve for X. If we subtract by 600 and divide by negative 4, we get that X equals 150. 150 is within our domain of 0 to 500, so that would be our only critical number. Now to determine when our revenue will be maximum, we're going to take our endpoints and our critical number and plug it into our revenue function. When we plug 0 into the revenue function, we get 200,000. When we plug 150 into our revenue function, we get 245,000. If we plug 500 into our revenue function, we get 0. We can see out of the three values, 2,450 would be our maximum revenue. But we should be careful about what the question is asking. They want us to find what I should make the price per room. Since my revenue is maximized when X equals 150, that means I need to increase my price by $150. My original price was $200, so my new price per room would be $200 plus $150, which equals $350. Now we're going to talk about unbounded and not closed domains. In our previous example, we saw that whenever our domains were closed, we can apply the extreme value theorem to guarantee the existence of our extrema. However, if our domain is unbounded and not closed, we can no longer apply the extreme value theorem. When this occurs, the function can still be optimized, but we just have to hope that there is one local extreme in the domain. When this occurs, this local extreme will be forced to be our absolute extreme. The concentration of a drug in a patient's bloodstream T hours after being ingested is given by C of T equals 52T over T squared plus 10. We're going to find when the concentration of the drug in the patient's bloodstream is at its greatest. We are already given the function that we want to optimize. So let's start by finding the domain of this function. Since T represents time, since the drug was injected, then the smallest T can be a 0 since T cannot be negative. What about the largest value of T? Since t represents time and time goes on forever, then t can increase without bounds, meaning our domain is the interval 0 to infinity. So here we see our first example of a problem where the domain of our function we're trying to optimize is not bounded. However, we can still try to optimize by finding a local extreme. To find our local extreme, we'll start by taking the derivative using quotient rule. Through quotient rule, we get c prime of t equals 52 times t plus 10 minus 52t times 2t all over t squared plus 10 squared. From there, we do want to try to factor and simplify our numerator, and we get that our derivative simplifies to negative 52 times t squared minus 10 all over t squared plus 10 squared. From there, we need to find our critical numbers. So we'll start by determining where f prime is undefined. F prime will be undefined when the denominator t squared plus 10 squared is equal to 0. However, as we solve for t, we run into t squared equals negative 10. Keep in mind, in calculus, we're only concerned with real values of our variables. So our derivative will never be undefined. So we'll determine where our derivative is equal to 0. So we need to solve the equation negative 52 times t squared minus 10 all over t squared plus 10 squared. Multiply both sides of the equation by t squared plus 10 squared, and we have negative 52 times t squared minus 10 equals 0. Divide both sides by negative 52. We get that t squared equals negative 10, which means t equals plus or minus root 10. However, keep in mind our domain is from 0 to infinity, meaning t is a positive value. That forces our only critical number to be the square root of 10. Now that we have our critical number, we need to test to see if that is going to be a local maximum or a local minimum. That's because if it's a local maximum or a local minimum, because it's the only local extrema, it would have to be the absolute maximum or the absolute minimum. There are two ways we can approach this. We could apply the second derivative test. However, if we were to apply the second derivative test, we would have to find the second derivative, which means we would have to use quotient rule again. So instead, we'll use the first derivative test. So now we'll make our sign chart for f prime. Keep in mind, since our domain is from 0 to infinity, we're going to have a hard stop in our number line to the left where t equals 0. We'll place our critical number root 10 and then pick sample numbers to plug into our derivative. Root 10 is a little bit over 3. So if I pick t equals 1 plugged into the derivative, we get that our derivative will be positive. However, if I pick a number bigger than 3, say 5, plug it into my derivative, we see that our derivative will be negative. Visualizing what this would mean for the graph. Wherever my derivative is positive, I know my function is increasing. So c of t would increase from 0 to root 10. But from root 10 to infinity, it will decrease. And it will continue to decrease as t approaches infinity. So here we can see a rough shape of the graph. And what would be our local extrema would actually have to be the absolute extrema, because the graph will never turn around to get back to a higher position. So when is the drug's concentration the greatest? That'll be when t equals root 10. Suppose a gardener wants to build a rectangular fence to fence off a carrot patch. The carrot patch is placed next to an already built wall that is 10 meters long. The gardener will not place any fencing by the wall. If the farmer wants the area of the carrot patch to be 120 meters squared, then what is the minimum amount of fencing needed to enclose the carrot patch? Since this problem involves geometry, we should start drawing a picture. We'll let the blue line represent the wall that we're not putting any fence against, and we'll let the red lines represent the sides of the fencing. Because we're trying to optimize the amount of fencing used for a fixed area, we should assign variables to the sides of our fencing. We'll let x be the length of fencing parallel to the wall, while y will be the amount of fencing vertical to the wall. Since we're trying to optimize how much fencing is used, we should write a formula that would calculate the fencing. Since our garden is a rectangle, we know parallel sides of a rectangle are the same length. So there'll be two sides of length y with one side of length x. So the amount of fencing used will be f equals 2y plus x. Since our area of the carrot patch is fixed, we should also write down the formula for area. Area we know is length times width. So the equation relating x and y is 120 equals xy. From here, let's start thinking about our range of values for x. Since our area is fixed and it has to be 120, can we make x 0? No, because if x is 0, the area would be 0. So we have to have that 0 is less than x. What is the most I can make x? Well, remember in the problem, I'm not putting any fencing against the wall, and the wall is 100 meters long. If x is greater than 100 meters, my horizontal side would stretch beyond the length of the wall, in which case I no longer have an enclosure. So the largest possible value of x would be 10. So 0 is less than x would be less than or equal to 10. As for y, because we have the equation 120 equals xy, the larger we make x, the smaller y has to be. So y would be at its smallest when x is at its largest. Since we've already determined that the largest value of x is 10, then the smallest possible value of y will be 12. As for the upper bound, because we can make x infinitesimally small, that means y can be extremely large. So there is no upper bound to y because x can get so close to 0. Now we want to write our fencing equation as a function of a single variable. Since x has a bounded interval, let's write our function in terms of x. So in our area equation, we'll solve for y. When we divide by x, we get y equals 120 over x. Now we can plug that into our fence equation, and we get that f of x equals 2 times 120 over x plus x. Simplified, we get that f of x equals 240 over x plus x. The domain of our function, we've already determined to be the range of x. Now we'll take our derivative, and we get that f prime of x equals negative 240 over x squared plus 1. Now to find our critical numbers, first we should see when it's undefined. Well, f prime would be undefined when the denominator x squared is 0, which means x equals 0. But is it possible for x to be 0? No. So we throw x equals 0 out as a possible critical number since it's not in the domain. Now we set our derivative equal to 0, and then we can solve for x. And when we do, we get x equals plus or minus the square root of 240. It's very obvious that the negative square root of 240 does not fit in the domain of our function. But what about the positive square root of 240? If you approximate the square root of 240, you can see that it is bigger than 10. So neither the square root of 240 nor the negative square root of 240 are critical numbers. So it turns out there's no critical numbers to our function under this domain. Can we still optimize though? Well, to see this, let's make a sign chart. So we'll make our sign chart placing 0 and 10 on the number line. Now we're not going to go beyond 0 and 10 since our domain is between 0 and 10. Now, there are no partition numbers to plot within this number line since none of our partition numbers were in the domain of f of x. So picking any number between 0 and 10, plugging into our derivative, we get that our derivative is negative from the interval 0 to 10. What does that mean graphically? That tells us f of x decreases on its entire domain. Now, what happens at 0 or points close to 0 doesn't matter. But we know at 10, our graph would have a closed dot on this domain. So x equals 10 will minimize the amount of fencing used. Since I know x equals 10 minimizes the amount of fencing used, then our answer will be f of 10, which equals 34. So the smallest amount of fencing we'll need to create our carrot patch is 34 meters of fencing.